So in the previous videos, we talked about double displacement reactions, specifically precipitation reactions. Being able to determine the products of a double displacement precipitation reaction, and from that molecular equation, writing the total and net ionic equation. Now we're going to focus on the other two subsets of double displacement reactions, specifically acid-base reactions and gas evolution reactions. So the acid-base reactions that we are going to deal with in this course can generally be called neutralization reactions. Okay? Those are reactions where you have an acid reacting with a base to give you water and a salt. So just to remind you, in general, an acid is something that when dissolved in water produces hydrogen ions, sometimes also called hydronium ions. There are monoprotic and diprotic acids. Protic means proton or hydrogen ion. Talk a lot more about diprotic acids and weak acids in Chem 2. You also talk a bit more about bases, weak bases in Chem 2. For all intents and purposes for Chem 1, you can think of a base as something that when you dissolve it in water or in aqueous solution, you increase the amount of OH or hydroxide ion. And we gave you a list in a previous video of the strong acids and strong bases that you need to memorize for this chapter, because you're going to need that information when predicting products of neutralization or acid-base reactions. So basically this slide just says what I said before, that generally when solutions of an acid or a base are combined, specifically strong acids and strong bases, you always get liquid water and some sort of salt, some sort of ionic compound. That is the general format for a neutralization reaction. And so we can take, just like we did with precipitation reactions, we can take that molecular equation and write an ionic, a total ionic, and a net ionic equation. Remembering that species that are aqueous get split into their cations and anions. So for this total ionic equation, I see three species that are aqueous, and so those three species are going to be broken up into their corresponding cations and anions. If you remember, we said things that are pure solids, pure liquids, or pure gases stay together, so that liquid water stays together. So that net ionic equation, after we cancel out the spectator ions, which I'll get my pointer here in a second, well, after we cancel out the spectator ions, essentially leaves us with hydrogen ion reacting with hydroxide ion to get you liquid water. So you should feel comfortable, given a molecular equation that's an acid-base reaction, predict the ionic and the total ionic and the net ionic equation. Finally, our gas-forming reactions. Those are another subset of double displacement reactions. We still predict the products of those reactions using our double displacement scales, the cation of one pairing with the anion of the other. What makes gas-forming reactions unique, as opposed to them forming a gas, is that the gas that is formed in these reactions comes from an intermediate that is unstable. And when that unstable intermediate decomposes or breaks down, it is that decomposition that produces the gas. We're going to do some more detailed examples in the next video, but in this particular example, if I have sodium hydrogen carbonate reacting with this acid, which I would not expect you to name, it's oxalic acid, the sodium is going to pair with that oxalate anion, the hydrogen with the HCO3. Your product, carbonic acid, H2CO3, is an unstable intermediate which breaks down to give you liquid water and carbon dioxide. So the products of this particular gas evolution double displacement reaction are this sodium salt liquid water, and carbon dioxide gas. So you may think, well, how can you determine if a gas is going to be produced in a double displacement reaction? These are the rules that are used when determining if a double displacement reaction produces a gas. It essentially depends upon the identity of your reactants. If it's a carbonate, sulfite, ammonium, sulfide, or cyanides. We will practice using those rules in the next video when we will predict the balanced molecular equation for 4 gas evolution reactions. So I would encourage you, before listening to the entire next video, to try those 4 examples on your own. We will go over them and the answers in the next video.